yeah, so it's a great pleasure to be here. It's my first conference in person in like 2.5 years, so it's very exciting. Yeah, so I want to tell you about a little bit about Floer Theoretic. Well, the title of the talk is Floer Theoretic Invariants of Three-Manifolds and their localization. Yeah, so let me tell you a little bit what the general idea is. So I guess so is this large enough, or should I go larger? Good. Okay. So the general paradigm, and this is the idea this learned in the 80s. Is that you know, so one can define very subtle invariants of three manifolds by counting solutions to certain nonlinear PDEs arising in mathematical physics. Okay, so we're interested in low-dimensional topology, let's say, and the main problem is like given a three-manifold, try to understand the properties, try to classify them, and there's classical invariants coming from algebraic topology or something more suited for three-manifold, like surgery theory or these kind of things. But yeah, one of the big revolutions in the field came in the 80s when Floer and other people realized that you can look at certain differential equations, and if you count the solutions, somehow you get some very subtle invariants. Okay. Yeah. So let me compare this with a slightly more classical thing. So I guess I added the word nonlinear for a specific reason. So you should compare this with the following. Okay, so if you have a manifold, closed manifold, let's say, with a Riemannian metric, then you have a nice differential operator, which is the Laplacian, acting on let's say differential forms. Okay, so and if you look at and this is a linear operation. Okay, so this is the Laplacian. Okay, and one of the key, one of the very cool theorems of Hodge is that the kernel of the Laplacian, is always isomorphic to the cohomology of your manifold with real projections. Okay, so the space of solutions to these differential equations is a vector space, and it doesn't depend on the metric you choose. So it's a topological. Okay, this is some kind of example in which by looking at solution of differential equations you can recover some topological invariants. It's not a particular subtle one, right? It's just the real homology. But yeah, and one very important thing is that this, the differential equation depends on the metric. But if you change the metric, just because of this, the dimension of the space of solution doesn't change. So that's an important thing. So this is independent of this. Okay, but it's dependent if you do something more slightly different. So if you look at let's say you add some perturbation, so alpha perturbation. Well, the space of solution changes dramatically, so you cannot get you don't see your topological invariant anymore if you change your equation a little bit in the wrong way. Okay, so it's an interesting thing because it doesn't depend on the metric, but it's not that robust, meaning that if you perturb it in the wrong way, then I guess I have no idea. Okay, we don't know what this is in general. Okay, so even if you add a constant, let's say, this becomes a completely different equation. The space of solutions changes completely, so we have no idea what that is in general. Okay, yeah. So the idea of Floer is that some special equations are much more robust in the meaning that still we will have this property that in our case, in Floer's case, so Floer is that here you have two data, so you have the solutions to your PDE that we're mentioning, the space of solutions. This depends on your choice of metric and perturbation. Okay, but then and this is similar to this situation, but somehow you can do some manipulations to this. In particular, if you do some algebra, you get topological invariants. Okay, and you get some kind of homology. Because in certain situations there are equations which are much more robust than what we would expect. So even if you change all the things that you get, all the data, somehow some properties of this space of solution really doesn't depend on what you chose. So you really get some topological in there. Okay, so I'll write this for now. Sorry, I need to think about. Should be fine. We can take it down. Okay, I'll do like this, and then yeah. So I guess the main example that I will need today, that I'm. Okay, so I guess the conference is called Geometry, Topology, and Algebra. Sorry, I'm not in the frame. Geometry, Topology, Algebra. So I will not write any equations. But yeah, I'll just tell you the names of the equations. So we're interested in the Cyber-Witten equations. Okay, and if you look at a Cyber-Witten equation, this involves these are equations coming from gauge theory. So the mathematical language that describes stuff like photons, electrons, this kind of stuff. Gauge theory. Okay, and from this equation, if you count the solution, you can define certain invariants. So this is on a three-manifold, and you can define these invariants called manifolds of homology. Okay, and this is due to this was defined by Horkheimer and Kropp. Okay, yeah. So the very interesting thing is that our equations are very robust, meaning that if you change g and alpha, these are some kind of things that you can wiggle a bit in these equations. Well, the result won't change. So here, at the beginning, maybe we would think, maybe we perturb it a little bit, but it's interesting to pick very large perturbations, and you get very interesting things if you do very large perturbations. So if you take, so if you pick what is called a contact form, alpha, if alpha is a contact form, so it's a one form for which alpha wedge d alpha is a volume form. Okay, this is a kind of geometry that's related to studying, dynamical system related to classical mechanics. So you can think of, the the motion of planets or the the pendulum or something like that. Yeah, so you get the equation somehow you can perturb, and the equation somehow becomes slightly different equation in the large limits. Some large perturbation. Okay. Yeah, and what you get is the equations that you get are like counting periodic orbits of some special dynamical systems. Okay. Is it still big enough, or should I write bigger? Okay. Good. Yeah. So this is called dynamical system that come from classical mechanics. So evolution of mechanical systems, very very complex mechanical system. Yeah. From here, this is another kind of nonlinear differential equations that arise, and from here you get if you do this procedure of taking Floer homology, you get another topological invariant called embedded contact homology. Why? This is due to touching. Okay, so here we had our form, and we take some special form. We take a very large perturbation, and we get some other equations, and we get some other invariants. And of course, because things were supposed to be the same under perturbation, this would turn out to be the same invariant. Okay, and then you can take a very special G metric, large perturbation. Well, what you get in the end is another set of equations. This is like intersection of Lagrangians in a symplectic manifold associated to Y. Okay, so we had two things to play around for our equation. One was some kind of metric, and one was this other perturbation alpha in one form. And in one limit, we get some other new interesting equation related to dynamics. In these other limits, we get some other interesting equation related to intersection of things in some interesting space. Okay, so if you do this procedure that I was telling you here, what you get is what is called HFY. This is called Hager-Floer homology. And this is due to okay, and this is Hutching. Sorry, this is called embedded contact homology. Okay. Yeah, so this is the big picture. So this is the thing I'll keep upstairs. And that's gone forever. So hopefully I'll get to some. Yeah. So yeah. So I guess if you've ever been to a talk in Floer homology, you always hear, oh, there's this version and this version and this version and this version, right? They're always, you might ask yourself, how did people came up with all these versions? Well, the invariant is really only one, and then if you take limit for these various parameters that you have in your theories, well, you get different equations that are related to different geometric objects. And so in one case, for the written equation, you're counting this thing called monopoles. In one case, you count these periodic orbits, and here you count these, intersection points of Lagrangians. But really, these are always the same. At the end of the day, if you do define things correctly, you should always get the same vector. Okay. Yeah. Any question? Yeah, so let me just remark that this is, just a heuristic picture. So remark This is just a heuristic picture. Okay, and any of these kind of different equations that we might end up looking at has their own set of difficulties that you will need to try to understand in order to define these invariants. And then even if it's clear from a heuristic point of view that these should be the same invariants, that's also very hard to show. So I was trying to do the computation yesterday. So I think proving that these things are well defined and showing that they're isomorphic, it's about 5,000 pages or something. So I think I might be something, but it's about 5,000 pages to show well-definedness. And these are all isomorphic. Okay, and the work about being isomorphic is due to many people, I guess. So the definition was the fact that it was defined is not the names I wrote, but Colan, Honda, Okay, but let's assume that these are all work and they're all well defined and they're all isomorphic. Then you have a very cool tool because you have one way to understand stuff about one set of equations if you understand stuff about the other set of equations. So you can think of this diagram that I wrote for you is like some kind of Rosetta Stone that translates theorem about intersections of Lagrangians to theorems about periodic orbits, or theorems about monopoles to theorems about intersections of Lagrangians. Okay, so yeah, and in particular, if you prove something cool in one set of this equation, you can try to see what are the implications for the other set of equations. Okay. Yes, I guess I'll just say the thing that were like very rich interpret. Okay, in particular, somehow there's some structure which is apparent in one set of equation, and you might not see it at all in why that you might say something like that in the other set of equations. Okay, so this brings me to what I was telling the title of my talk. So I guess one of the key features of the Seiberg-Witten equations which is not, which is not apparent. Somehow this S1 symmetry gets lost when you take these large limits, so you don't see this kind of symmetry neither in the periodic orbit setup or in the Lagrangian intersection. Is that they admit an S1 symmetry. Okay, so you can think of, there's some kind of circle action on the space of objects on which the equations are defined, and this preserves the equation. So yeah, so this is a symmetry that is clear in the Seiberg-Witten world. In the other situation, is not as apparent, maybe. Okay, so in particular, this tells you that once you have here I was just telling you that Floer, you look at solutions and you get some homology. Now we have this extra thing, which is this S1 symmetry. So in the presence of symmetry, the natural thing to try to do is try to define some kind of equivariant homology. Okay, so this should be S1 equivariant theories. Okay, so yeah, so let me tell you a little bit what this equivariant homology is. Any question? Yes. Okay, so yeah, you can think of. So I guess let me just equivariant. This one equivariant. cohomology. So okay, so usually, it's a kind of refined version of cohomology that you study for spaces which come with an action of a circle. So, so let's say, for us, for simplicity, let's say you have a circle acting on a smooth manifold, let's say. Yeah, by the way, this smooth manifold is not Y. So Y, is just a three-manifold, so there's no such action. This M is some kind of manifold associated to Y on which there's some symmetry there. So this is not Y in our situation. Yeah, so you can think of something like this. I guess this is the basic example of an interesting space with a circle action. So it just rotates the sphere. That's the interesting action, and it has two fixed points. Okay, so so one thing is that you would like some kind of cohomology thing that captures the fact that this is an interesting action. It's not like, for example, a free action. There's these two fixed points. Yeah, if you quotient this thing by the action, you just get an interval. So that's somehow not the right thing, right? So because S1, S2 mod S1 is contractible, is interval. So just looking at the quotient, you lose a lot of information about direction. So this is not a good thing to do. The interesting thing to do is like somehow try to convert this action, which is free, which has these fixed points, into a free action up to homotopy. So what you can do is like, you can multiply your space by S infinity. S infinity is the infinite dimensional sphere. So, this has a natural S1 action by multiplication by complex numbers, and it's contractible because, well, it's the infinite one, so there's no homotopy group. It's contractible with free S1 action. Okay, now here, the action S1 acts diagonally, so I can quotient. And the nice thing is that the diagonal action, now it's free because it's free on the second part. So now it's a much nicer way to take the quotient because it's a free action. So this is S1, and by definition, this will be the equivariant homology of the space. Okay, this is the definition of your equivariant. Okay, so it's a homology of a space with an action. Yeah, so one very nice thing is that one important property of this kind of object is that it's functorial for S1 maps. Okay, so if you have an M prime and you have an action on both that preserves the S1 action, then there is an induced map in equivariant homology. In particular, you always have a map from from M to a point with a trivial action. So you get a map in equivariant homology from the homology S1, the point, to the equivariant homology of your manifold. Okay, but if you plug in a point here, what is object here? This is just, by definition, this is just the homology of S infinity mod S1. Okay, the point here doesn't change anything, and this is just if infinity. Okay, so this is the polynomial ring join U, and this has degree U equals 2. Okay, so if you have a space with S1 action, the equivariant homology always comes with a homomorphism ZU to it. So this is always a module over Z adjoint U. Okay, so this is why from this perspective, it's clear that these invariants, that the Floer homology invariants of three-manifold should not just be modules, so should not just be groups, but they should actually be modules over this ring here. Okay, so yeah, and in particular, this is clear from the Seiberg-Witten perspective because the equation has this S1 symmetry, and in the other two versions, you have to you can still define this ZU action. That's it's kind of it comes in a very different way, this ZU action, but it's inspired from this. Okay. Yeah. Any question about this? Yeah. Yeah. So of course you can imagine that this is a pretty complicated object to define because already for a point we can complicated polynomial ring. If you take any manifold, then it becomes something very complicated. But yeah, and also maybe I forgot to mention, this Seiberg-Witten invariants. I haven't told you about yet what you can do them for, but they're powerful, but they're also very hard to compute because if you look from the definition, for example, it's you have to solve some differential equations on the manifold and try to hope to compute these invariants. Right? Yeah. So one tool that is useful in portfolio situations is this thing called the localization theorem for equivariant cohomology. Yeah, so localization theorem. Okay, so I'll make some simplifying assumption, which is the case for the equation we're interested in, the Seiberg-Witten equations. So suppose the stabilizer of a point is either the whole S1, so it's a fixed point, or is the trivial element, so the action is free. Okay, in general, you might have things that stabilizer in general is a subgroup of S1. So here I'm just saying, oh, it's either the trivial group or it's everything. Okay, so this is what happens in the case of the Seiberg-Witten equation. Then, yeah, so because this is a module over U, you can localize U. So the cohomology of M, and I invert U. Okay, so this is the localization, the algebraic localization. Okay, so in our situation, what happens is that you decompose your module as a module, and you kill all the U torsions actually. And this is the U inverse tensor, just the regular cohomology of the fixed points. Okay, so these are Laurent polynomials, so this is just the fixed points. Okay, so the idea here is that once you forget about the U torsion, which is algebraically what this inverting U does, the equivariant cohomology becomes very simple, and it only depends on the fixed point sets of the action. So in this case, it only depends on two elements. Okay, so in general, this object is very complicated. So it's a new thing, but if you forget about the U torsion, then it's very simple. You just have to look at the fixed points of your action. Okay, and this is a very fundamental theorem in the theory of equivariant cohomology. Okay, and I want to tell you that this is a powerful tool in third theory. Okay, and that's because the idea is that this object here, which is your Floer homology, is very complicated. But this thing here, in general, one should expect to be very simple. Okay, so So I guess so. In all these third theories, once you invert y, should be simpler. Stop. Okay. Okay, just because they only depend on some kind of simpler algebra, just a fixed. You don't need to know the whole S1 action. You need to know S1. Okay, let me just tell you some basic example in which this thing can, a basic case in which one can try to apply this kind of philosophy in the Floer homology setup. Yeah, so as an example, I guess, let me just say a little. It's very complicated. Okay, so any kind of information you can get about it is very good. Yeah, so let me just give you an example. So suppose your manifold is a rational homology sphere, so B1 is 0. Okay, this is the same as saying that H1 of Y is finite. Okay, then what you can show is that if you, I guess, if you invert this in any of the theories, so I'll just state things in HM, but you can do everything in your favorite theory. HM of Y. Well, this is just a Laurent polynomial ring, and if you take cardinality of H1 YZ copies of it. Okay, from this point of view of this theorem, it's saying that you can think the fixed point set is just so heuristically fixed point set, and the fix is points. Okay, and this is actually the way you prove it. If you look at the equation, and the fixed point set is just this number of points, and then the localization theorem has this. Yeah, so why is this useful? I told you all these are. Let me just tell you some very concrete way this kind of result is used. Yeah, so I guess one can use this. I won't go into the details. This is used to define numerical invariant of Y called correction terms. Okay, so these are some kind of numbers that you can, we have the whole complicated equivariant homology thing, but at the end of the day, you can just extract a bunch of numbers. And these are very powerful numbers. So let me just tell you a very concrete application. So now there's the moment of truth in which I'll try to draw a knot with 8 crossings. Okay. Usually it doesn't close up. So, okay. Yeah. Okay, it looks much nicer in my notes, but I'm slowly getting there. Okay. Okay, so this is the not A10. So this is looks correct to me. Okay, so these are simple knot with 8 crossing. And not theory is a very concrete question. Like if I give you this loop and I tell you, how many crossings, I want you to make it into the trivial loop. But of course this is a non-trivial loop. It's not obvious. But yeah, the question is like, how many times do you need to change crossings in order to get to the trivial loop? Okay, and the question, this seems like a very, basic question, but this kind of question is very hard in topology. And there's classical tools like Alexander polynomial, these kind of things. But yeah, somehow they all fail for this object. So really, I think only in the early 2000s, Oswald Szabo showed that this has a knot in number 2. Okay, so this is in the 2000s. Okay, using this kind of numerical invariant arising from Floer homology. So with all the previous tools we had to study knots, we have lots of them. People didn't know to show that you cannot, one crossing change, not in this diagram, but just in any diagram, is not enough. But yeah, finally using Floer homology, in particular these correction terms, one gets one was finally able to prove it. Yeah, and the real way, the key point behind the definition of these correction terms is this computation, which is the localization theorem in disguise. Yeah. Yeah, this one action is in the it's in the configuration space of the manifold. So it's in some infinite dimensional space of connections and speed of those connections. Yeah, I don't think this. I don't know if this not has its fiber. But yeah. Yeah, this was I think very cool. We do all this crazy stuff, and it turns out have very concrete applications to study and not. Yeah. Okay. So let me tell you. So this was one direction. So so really Oswald Szabo worked in the Hegel-Floer homology world, where computation are somehow easier to do, and so they were able to compute these correction terms. Let me tell you another interesting application of these ideas in the other way. So trying to look at these periodic orbits of dynamical systems. Yeah, so I guess this is the theorem of Kronecker-Mrówka. Okay, and then Littmann later in a different setup. What they showed in the 2000s, like 2010s, this theorem. That this localization of y is never trivial. Okay, so it could happen for some reason that for example, if this Floer homology was always a torsion U module, then this localization would be trivial. So it turns out that this is even if you invert U, there's some interesting object here. So it's not it's never a torsion U module. Yeah, so I want to tell you a little bit about this. So this is, but yeah, so this computation was done in Sager-Witten theory. But of course, I was mentioning before, that all these theories are interconnected. So if you can say something cool about one, then you can translate this theorem in another theory and get some cool theorem there. And this is what what Tubbs. I use this to prove the Weinstein conjecture, which is a conjecture about this periodic orbit. So let me just, I didn't define anything properly. I guess the Weinstein conjecture. In dimension 3. Okay, if you have y alpha contact manifold, the red vector field has a periodic orbit. Okay, so it's a theorem about. I won't define what red vector field has, but you get, once you're in a contact manifold, you get a special dynamical system. And once you have a dynamical system, the basic question is like, can you always, are there periodic orbits or not? And using this circle of ideas, you can show that this specific dynamical system, which is related to classical mechanics, always has a periodic orbit. Okay, so this is just to showcase some interesting relations between. Once you know something about one theory, you can get theorems in the other theories. Because you're studying very different equations, so maybe one equations are simpler and the other more complicated, but you can say something. Yeah. Okay. Yeah. So I want to tell you actually a little bit more about this theorem. In particular, what they do is give an interesting. Actually, you can actually compute this whole localization. And if you look at the equation, it might be a little very surprising that you can actually do it. But it turns out that this only depends on some very classical thing. So turns out, we did all this work. It turns out that this particular thing is not that subtle, I guess. So recall. So I guess here they give computations in terms of so they don't. I guess what they do is like they don't do the computation. But, these are Z modules, but you can look at over fields. So over Q for Kramer-Mravka / Z to Z in terms of the so-called intersection triple cup product. Okay, what's the triple cup product? Well, the triple cup product is like, this is cup 3 of y. It is, you look at the third exterior power of your integral homology. This is again on the manifold itself. So this is just on your manifold. And this is a map to Z. And you take, the wedge of 3 one-dimensional homology classes, and you send it to their cup product. Their triple cup product. That's where the name comes from. And then, these are all degree 1 classes. So this is in H3. And you evaluate it on Y. Okay, so this is a classical invariant of your three-manifold. It's just, you just need a cup product to define this. And this is also called intersection ring. Intersection. I guess this measures. If you think about cup product in terms of intersections of cycles, this measures intersections. Okay, so if you have 3 surfaces in your manifold, you expect the intersection a finite number of points. So this is encode that algebraic. Okay, how much time? 10 minutes. Okay, so I'll just briefly move on. Yes, I guess so. You can define, so the key theorem is that you can compute this invariant, which is, if you don't invert U, you get all this U torsion, and that's a very subtle object. But yeah, once you invert U, the thing only depends on this algebraic topology thing. So somehow you lose a lot of information, But that means that it's much more computable because it's a very, it's not easy, but you can compute it. Okay, so let me just describe how this computation goes. Yeah, so the key point in the point of view of the localization theorem. Okay, so suppose you have S1 acting on the space of solutions, the Seiberg-Witten equations. Okay, so the Seiberg-Witten equations have this S1 symmetry. It turns out that if you lay, in general, you cannot solve the Seiberg-Witten equations, and they're very complicated, to understand. But it turns out that the fixed point set of this action is very easy to understand. So fixed point, so fixed locus. Well, this is just the set of homomorphisms from the pi1 of your surface to u1. Okay, and this is h1 of y with our coefficients modulo h1 of y is the coefficient. So it's a torus with dimension u1. And I guess here, to be precise, here I will need to fix, I won't even say what it means, but to fix a torsion species structure. Okay, so the fixed locus turns out to be very easy, just a torus, very very simple object. Yeah, so you can try to, so in some sense you expect the homology, the localization to depend only on the homology of this torus. So here is where the analogy breaks down a little bit. There's a little extra data you need to add. So, but let me just tell you what the result is. So the homology, of this torus, the space of solution. Well, this is the exterior is the Floer algebra of lambda 1 y with z coefficients. Okay, and so in particular, our triple cup product. Gives me a cohomology constant. It's an element. It's in the dual of the homology, so it's a cohomology constant. Okay, and you get the natural evaluation map from HK of the torus. You can contract like this. You have a 3 form, and if you have a K form, you can all contract it in contraction. Okay, and the theorem is that by Kronheim, Rocca, and Lidman, is that, well, I said the version over Q. So the inverse HMY, and here I need to pick this torsion species structure. But if you don't know what it is, that's perfectly fine. Is the homology of, I guess the cohomology of the torus tensor Z U inverse. So this is what you will naively expect from the localization theorem, just because this is the fixed point set. So the localization theorem will tell me that this is this. But yeah, it turns out that here the analogy that I was giving breaks down a little bit. So here you need you pick this map cup 3y times u4. Okay, so this is a map that squares to 0, so it's a differential here, and the cohomology of this is the localization of the homology over with Q coefficient. So Okay, and Lindman showed it with the two coefficients. Yeah, so I guess let me just add in more examples. So this is remark. This is smaller than one would expect. Okay, but yeah, yeah, but still, it's a very concrete computation. If I give you a three-manifold, this is a classical algebraic topology invariant, so you can compute this over there. Okay, so let me just conclude with a discussion about the integral torsion, which is so let me just mention that, in general, so these theorems are cool because you can use them. Well, the whole computation of the fields of characteristics 0 and 2. But yeah, I guess the point is that in general, this you can, in some simple example, you can compute that this U inverse. If you don't tensor over Q, so with Z coefficient, has a lot of Z torsion. Okay, so you don't even have to go to very exotic objects. For example, you just pick Y is surface times the circle. Sorry, surface times the circle of genus G large enough. I think G bigger or equal than 3, you get 2 torsion. And if you go G bigger or equal than something else, you get 3 torsion. Well, I guess by induction, I would expect that you get any torsion you want, but I don't know. It's a linear algebra problem in this situation, but yeah. Has 2 torsion. Has 2 torsion. Yeah, so it's not obvious how to this computation doesn't give you the whole story. So I just want to state one result. We somehow in joint work with Mike Miller, Eismeier, we last year, so 2021, we did a full computation of inverse Y over Z. Okay, and the idea is that you get the same object, so you will get T tensor Z U inverse, and then you get the first term is the same, and then you get some additional complicated extra terms. Okay, that you can compute the term in by cup 3 of Y. Okay, so in general, if you want the computation over Z, you have to add these extra terms that you can still compute them in terms of the triple cup product. And I won't say much about there's no time. I guess the funny story is that the funny thing is that to prove this theorem, really, we just went back and looked at the chain complex of the torus and realized that it's super complicated. We spent all this time doing cool things with PDEs and stuff, and then we don't really understand the chain complex of the torus in general as a BG. So yeah, we spent months and months thinking about the torus, the simplicial cohomology of the torus. That's super complicated, and somehow because that's a non-commutative DGA, if you do a lot of algebra, you end up with. So these extra terms somehow measure the fact that this object is commutative at the homology level, but at the chain level, it's not a commutative algebra. So it's really the chains on the torus are very complicated. I guess that's mine. And I'll end with this. Oh. Oh, yeah.
So, maybe it takes us so much far afield, but you constructed this circle equivariant cohomology because you sort of had in your back pocket some good space for a circle map. How general is that? If I have some group action on some other space, can you give me some group action equivariant cohomology for that as well?
Yes, I guess so. The question, I guess I'll repeat it just for the audience on Zoom. So then the question was like, I did S1 equivariant homology because I get a space with S1 action. In general, yeah, if you have let's say a compact Lie group acting on a space, there's an analogous theory of equivariant homology. You just need to replace S infinity by, the definition is the same, you just replace S infinity by a contractible space on which GX freely, that always exists, and then that gives you the so-called Borel equivariant homology of the space. Yeah, and I guess there's other situations, even in this setup, where you have your naturally steady equation, for example, with SU2 symmetry or this kind of thing. So these ideas that I discussed here for these equations, you can use them also in other setups. Yeah. Oh.
Can you remind me your Hawk example? Where was the threefold? The three-manifold.
Sorry?
Yeah, so I thought at the beginning you said the theory was called three-manifold.
Oh yeah, sorry. So the question is like, yeah, I briefly mentioned this example with the knots. It was mostly just to draw a knot. But yeah, the idea, the three manifold you studied is invariants for is the branch double cover. Yeah. So I guess there's this very cool trick that if you have a knot in number 1, the branch double cover is surgery on a knot in S3, and this correction term give you obstructions to that. So yeah, it's a very long story. I compressed it in one blackboard. Yeah. Oh yeah. So the question is like, do you have analogous stuff for Donaldson-Thomas invariants? I never really understood Donaldson-Thomas theory, unfortunately, so I don't know. Yeah. Oh, sorry. Oh. Yeah, here. Yeah. Yeah, so the question is like, I didn't say that, but these are all somehow functors. And the question is like, do we have result about maps? I mean, yeah, it's work in progress. Yeah, so I think under a certain assumption on the cobordis, I think, yeah, we're writing up some stuff that allows you to compute the induced map on a cobord. Yeah. Negative definite cobordis. Yeah, if there's no negative definite, the map is 0, but once, so yeah.